Welcome back, students, to the next lecture that we have in as far as the refraction of light is concerned. Okay, so here as you can see that I have drawn the diagram that we had in case of refraction of light through a rectangular glass slab. So I have once again drawn it because there are a few factors on which this particular lateral shift or the lateral displacement depends, so that we are going to discuss just now. But first let me recall for you all the diagram that we had drawn. This is a rectangular glass slab that I have drawn, and there is obviously air on either sides of it. Okay, so you can see the incident ray. This is the ray that was traveling in air initially. Okay, so this incident ray is making an angle I, which is angle of incidence. Okay, and then after that it undergoes refraction. Okay, so this is the refracted ray that we have, and it is again forming a refraction angle. Okay, at this interface the bending has been towards the normal because this is traveling from rarer to denser medium. Okay, now then again when this ray of light reaches the surface of separation once again, now this time the ray will bend again, but it will be away from the normal because it is coming from denser into the rarer medium. Okay, so based on that same concept, the same diagram has been drawn. This is a more properly labeled diagram. Okay, so this was the original direction of the ray, so I have produced that forward. Obviously the ray does not actually travel this path, it travels another path, so this is the final path that it takes. So these two appear parallel to each other, and this x portion is the distance between these two parallel paths, and it is this x that we are calling the lateral shift or the lateral displacement. Okay, so this lateral shift, as I already told you, will not be same in all the cases. Okay, you can have a number of variables in this particular process. You can take the glass slab in which the glasses are of different kinds. Then you may also have an increased thickness of the glass slab, or you may also take different colors of light that are there. Okay, so the factors which are affecting x value we are going to discuss just now. Okay, so as you see here, factors affecting x is nothing but the lateral displacement. So the first point obviously will be the refractive index of the glass that we are using, this glass, or it is also known as the nature of the glass. Okay, so obviously what will happen, more is the refractive index of the glass, there will be more bending. Okay, because refractive index value itself is indicating the bending capacity of that particular medium. Okay, so more the refractive index, there will be more bending. So when there is more bending, obviously you will have the x value also coming out to be more. Okay, then obviously the second one is the wavelength of light. Okay, so this particular point we are going to discuss in detail in a short while. As of now, you understand that the wavelength of light is associated with the color of the light. Okay, so as and when the color keeps on changing, we keep sending different colors of light, we observe that the value of x will change. How will that change? I am going to explain that in a short while. Okay, now angle of incidence or the incident angle. So this angle also, if you increase angle of incidence, you will find that the lateral shift or the lateral displacement also increases. Okay, so this is the third factor, and lastly we have the thickness of the glass slab, which is this T that I have labeled in the diagram. This is the thickness, as you can see. So logically, when you have a ray of light entering into the glass medium and bending towards the normal, okay, so this is the bend that has taken place. Okay, the more it keeps on moving in this glass slab, the more value of x you will get, because obviously since T is going to be more, the thickness is going to be more, this ray, refracted ray, has to travel much more distance if this T is more. Okay, and you can see that this, as and when this refracted ray is traveling in this glass medium, it is going away from this original path. You see, this was the original path, and as and when it is moving in this glass medium, it is going to go away from this particular original path. Okay, so if this thickness is more, it will travel more and it will get deviated more. Okay, so eventually what you will get in the end will be a higher value of x. Okay, so with increased thickness also you get an increased value of lateral displacement. Okay, so these are the factors that will decide the lateral shift or the lateral displacement. Now coming down to the wavelength of light, which is lambda, in detail, you can see there is a diagram that I have drawn over here. I have taken a rarer medium and a denser medium, okay, and I am passing two different colors of light at the same angle of incidence. Okay, so this is the violet light and this is the red light, and we see that this both are falling at an angle of incidence equal to I at the surface of separation. Okay, so since there is a change in the medium, the light will bend. Both rays of light will bend, but the bending degree or the degree to which they bend, degree by which they bend, or the angle of refraction is going to be different. As you can see, this light has also bent from its original path, and this has also bent from the original path. It is obvious that this has bent more. Okay, so now we are coming to the color aspect or the wavelength aspect of the ray of light. As we all know that the 7 visible colors that we have, they are violet, indigo, blue, green, yellow, orange and red. So the overall it is known as Vibgyor. Okay, and talking in terms of the wavelength, we will see. So the wavelength, although all these 7 colors will have different wavelengths, you can have a look about the exact values of wavelength for these colors in the book. I have listed the extreme ones, which is like for red color it is 8000 angstrom. 1 angstrom you obviously know is equal to 10 to the power minus 10 meters, and for violet light you have 4000 angstrom. So for the visible portion, the wavelength range is from 4000 angstrom to 8000 angstrom. So it is very obvious, you can see that the violet color has the least value of the wavelength, and it goes on increasing till we reach red. The red value, the red color has the maximum value of the wavelength. Now coming down to the relationship that I told you, for any wave motion we have V is equal to F lambda. Okay, and since the frequency is fixed or same, because the source of light is same, so we are left with V proportional to lambda. Lambda is the wavelength. Please don't forget, lambda symbol denotes the wavelength of the light or the color of the light. Okay, so V and lambda, they are directly related to each other. So what will happen if we move towards the left hand side in the color band? If we start moving towards the left hand side, you see the lambda value is decreasing, and it is in fact the least for the violet color. Okay, so if lambda is decreasing, obviously we will also decrease. Okay, so for the least wavelength color, okay, listen carefully, for the least value of wavelength, or for a color which has the least value of wavelength, there will be maximum drop in the velocity, because lambda is dropping to the maximum degree for violet color. Therefore the velocity drop for the violet color will also be maximum. Okay, so more and more is the velocity change or velocity drop, more is the bending. Okay, so now onwards you will say that as and when lambda drops, okay, the bending will be more. Okay, so this is the relationship that we will have to memorize, because based on different colors, when we take different colors, that means we are taking different wavelengths. Okay, so for the minimum wavelength colors, or for the least wavelength colors, which in fact is the violet color in the visible band, as you can see, violet color once again has the least value of wavelength. So least value of lambda will mean maximum bending. Why maximum bending? Because bending is actually a result of the change in velocity or the drop in velocity in this particular case. So as you can see, as lambda is dropping, the velocity will also drop. So the maximum drop in the velocity means maximum bending. Okay, so from now onwards, as a gist or as a conclusion of this entire thing that I am teaching over here, now onwards you will remember that for a color having least wavelength, the bending will be maximum, and for a color having maximum wavelength, the bending will be minimum. So wavelength and bending, they are inversely related to each other. Okay, so obviously having a look back at this particular diagram where I had taken the violet color and the red color, you can see that the violet and the red colors are at the extreme ends. Okay, so violet has the least wavelength, therefore the bending is maximum, and red has the maximum wavelength, therefore the bending is minimum. Okay, so based on the colors you can have a diagram drawn. Okay. Okay, so now coming moving forward to another small aspect over here. Now this is more or less logical for us to understand that whenever there is an incident ray of light, you can see that there is an incident ray of light over here which is falling at the surface of separation. Okay, now this is the surface of separation that we have. Okay, it is separating the rarer medium and the optically denser medium. So although in this particular chapter we are particularly studying refraction of light, which is the bending of light when light travels from one medium into another medium, but we must always keep in mind that this is not the only process that is going on. In fact, some part of the light gets absorbed at the surface also, whereas some part of the light gets reflected back also. Okay, so you must remember that there are a number of processes that are taking place. Since we are studying refraction in this particular chapter, so we are basically studying refraction part only, and we have not been showing the reflected and the absorbed part. Okay, so but then these processes are all taking place, and obviously you remember that refraction is a surface phenomena. Okay, whatever bending or whatever change in the speed of light that takes place the moment there is an encounter at the surface. Okay, surface of separation. So the moment the light finds that there is a change in the optical density of the medium, that very moment the bending starts. Okay, so this is the place where the bending happens. Okay, so refraction is a surface phenomena. Now there are two questions that I am going to pick up just now based on what we have studied. Question number 1, a ray of light passes from medium 1 to a medium 2 and it bends. Okay, so the situation is given, the light is entering into a separate medium and it is bending also. So that means refraction is taking place. Which of the following will change? Okay, now these are some of the characteristics, 4 characteristics or the properties you can say of light that are given. So you will have to tell us, or you will have to identify by applying a little logic that which of these will change as a result of this process. What process? The process of light passing from one medium to another medium. So will the speed of light ray change? Obviously, because of this change in speed of light only the bending takes place. Okay, so speed of light ray, you will put a tick. Okay, so this is going to change. Now coming to the next part, that is the wavelength. Obviously the wavelength also changes because the speed of light is changing. Speed of light and lambda, which is the wavelength I just now showed you, they are directly related to each other. Okay, so as and when wavelength changes, the speed of light also changes, or vice versa. So you have the wavelength part of the light also changing. Now coming to the C part, which is the intensity of the light. Okay, now light intensity, you can answer this particular part from the diagram that we have discussed over here. You can see that although the maximum or the majority portion of the incident ray is going into the second medium as refracted ray, but there will always be some part that will be reflected also and that will be absorbed also. Okay, so obviously there will be a result, or there will be a change in the overall intensity of light that comes into the second medium. Okay, so the intensity of light will also drop. Okay, so it will change. Okay, frequency is the only thing that does not change, because I told you frequency will depend upon the source from where it has been generated. Okay, so once it has been generated, the frequency is not going to change whether it travels into one medium or into another medium. Okay, So this was more or less a theory based question or a concept based question. Now coming to question number 2, which is going to involve numerical over here. So you see, find the refractive index of a medium in which the light travels with the speed of 2.5 into 10 to the power 8 meters per second. Okay, so you are supposed to find out the refractive index of a medium in which light travels with the speed of this much. Okay, so if we want to draw a diagram over here, you see, suppose this is the air medium and this is the medium that I am talking about. So let this be medium 2 and let this be medium 1. Okay, so obviously this will be the process. Why? Because you see, when we have the refractive index formula, refractive index of medium 2 with respect to medium 1, it is given by, if you remember, it was given by a formula, velocity of light in medium 1 upon velocity of light in medium 2. Obviously there was another formula, if you remember Snell's law, the refractive index equal to sin I upon sin R, but then since I and R values are not given in this question, there is a speed value given in the question, therefore we will utilize this particular formula. Okay, so now if we see, say, refractive index of our medium, which is this medium, with respect to the first medium is air, equal to, so we will have velocity of light in air upon velocity of light in medium. Okay, so this is the formula that we have. Refractive index value we have to calculate. So we must remember, even if the question does not give us the velocity of light in air, we will take it to be 3 into 10 to the power 8 meters per second roughly. Okay, this is, in fact, this exact value is for the light of for the speed of light in vacuum, but for air also it is more or less same. In fact, the velocity of light is maximum in vacuum. So this is the value that we have, 3 into 10 to the power 8 meters per second. Okay, and the velocity of light in our medium is already given in the question, so you will put that 2.5 into 10 to the power 8 meters per second. Okay, so this obviously the digits, the units are same, so they get cancelled. 10 to the power 8 and 10 to the power 8 also gets cancelled, so we are left with 3 upon 2.5. so you remove one place of decimal, you put a 0, so you will have 5 6s and 5 5s, so this comes out to be 1.2. Okay, so your refractive index of the medium is 1.2. So whenever you say refractive index of a medium, it is always in comparison to air as the first medium. Okay, so you can see that we have got the value of the refractive index of the required medium using the velocity ratio formula. Okay, so what this particular question tells you is that even when you don't, even if you are not given the velocity of light in air, you must remember that 3 into 10 to the power 8 meters per second. Okay, so for air and for vacuum we will take this value more or less to be the same practical. Okay, so coming lastly to the practical applications of the refraction process, there are some very common experiences that you might have had in your life. You see, this is a case of a coin which is placed in water and it appears raised, okay, raised from its actual position when seen from the air. Okay, so this is the air medium and this is some liquid or water, maybe this entire thing. Okay, and this is the coin that is placed right at the bottom. Okay, so this is the real position of the coin that you can see. Okay, now what happens is, for a person who is viewing from the air, suppose the person is standing over here, this is his eye. Okay, so he wants to view the coin from there at the top. What will happen? For viewing, there is obviously the need of an illuminated object. Okay, so this is the object that is illuminated. Okay, there must be light all around. Okay, so for this person to see this particular coin, there has to be light which has to fall on this coin and then light has to get reflected. So I am going to start from here. This is the coin. There are two rays. For image formation, minimum 2 rays we will require. So this is one ray that has started traveling from the coin, and this is the other ray that has started traveling. Now till the time they are traveling in the liquid medium, they will keep on following the same path. Okay, so they are moving straight, but the moment they encounter this surface of separation, now you see this is the surface of separation between liquid and air, or water and air. So there is a difference in the optical medium or optical densities that is observed. So what will happen? The ray will have to bend. Okay, now that bend, either it is towards the normal or it is away from the normal. So we know that this liquid or water is always the denser medium in comparison to air. So the light is going from denser medium to rarer medium, so it will bend away from the normal. So if we talk about this first ray, this was the original path and it has bent away from the normal. Where is the normal? This is the normal. Similarly, this was the second ray traveling. This was the original direction, but it has bent away from the normal. This is the normal for the second ray that we have drawn. Okay, so after getting bent away from the normal, now you see they are diverging. Okay, so their image has to be formed by forwarding, or you can say that by producing these rays backwards. If you see, this is roughly the way that you will produce it backwards, and similarly this, if you produce it backwards, something like this. Okay, so they will meet somewhere over here. Will they actually meet? No, the rays are not going to actually meet, because the actual rays are this. The actual rays are getting diverged as they are going. Okay, so in order to produce the image, in order to obtain an image, we will produce these two rays backwards with a dotted line, and you can see that they are appearing to meet at this particular point. So the image that will be formed will obviously be virtual in nature, but it will be formed over here. Okay, so the real coin, although it is placed over here right at the bottom, the person who is viewing from here, he will feel as if these two rays are coming from where? Coming from here. You see, they seem to originate from here and then they are traveling like this. So the person who sees from here in the air, for him it will appear that these two rays are coming from where? Coming from here. Whereas actually they came from here. They had actually bent during the process of refraction. So this is the case. Now, so after once we label it properly, you can say that this, you can say, is the real depth. Okay. This was the real depth of the coin. So what will be this much? This will be the apparent depth. Okay, so you can say this is the apparent. Apparent means what is visible to us. Okay, that may not be the reality. As you can see, there is no coin over here as such. The real coin is over here. Okay, so this is the real depth and this is the apparent depth. Okay, because this is the apparent coin, this is the real coin. Okay, so in fact, as and when we go along, we will establish a relationship also between apparent depth and the real depth and the refractive index of that medium. So with the help of a formula, we will get a formula later on. Okay, but as of now, you understand that a coin dipped in water appears to be raised. So it is raised when seen from the air. What is the reason why it is appearing raised? Because of the process of refraction. Similarly, you can have a number of other cases also. There is a small case over here that I have taken up. This is a small, thin, very thin postage stamp that is lying on the table, and on that postage stamp you have a thick glass. Okay, so the person who is viewing from the air, to him this postage stamp, which is right at the bottom on the table, okay, this is the table, it is lying right at the top on the table, okay, but it will appear slightly raised. So for a person who is viewing from here, the postage stamp may not appear to be here, it may appear to be slightly raised. Okay, so the ray diagram you can draw in this particular case also. Similarly, you must have seen that if you dip a pencil or a piece of ruler into a bucket full of water, you will see that from the portion which is immersed in the water will appear to be slightly bent. Okay, so again the process responsible for that is refraction of light. Okay, so we will stop here. We will continue from the next lecture. Thank you.